consider the following system of coupled differential equations. A. Find the eigenvalues and corresponding eigenvectors of a matrix. So how to find the eigenvalues and the corresponding eigenvectors? Should consider determinant of the next matrix, negative 4 minus lambda, 0, 3, negative 2 minus lambda. And this determinant must be 0. How to find the determinant? It's this product minus this product. So it becomes minus 4 minus lambda multiplied by negative 2 minus lambda is equal minus 0 is equal to 0. You can see that we can factor out minus here and factor out minus here. It's plus, or it actually doesn't matter because product is equal to 0. So we can rewrite to be more easier 4 plus lambda times 2 plus lambda. It's not necessary actually, is equal to 0, and let's expand 8 plus 2 lambda plus 4 lambda plus lambda squared. To get a quadratic equation with respect to lambda, it becomes lambda squared plus 6 lambda plus 8 is equal to 0. You may use a sum and product rule or discriminant. So let's try sum and product rule. Since a is coefficient in front of lambda squared is 1, it will be useful. Sum and product rule, let's try. Otherwise we can do discriminant. It can be applied for every problem. So sum is minus b of a, so negative 6 product is c of a, so it's 8. To get product of 8, it may be what? 1 and 8, negative 1, negative 8, but we need sum of negative 6. So what? 2 and 4, or negative 2 and negative 4. Yes, it's correct. So lambda 1 is negative 2 and lambda 2 is negative 4. You can see product is 8 as required, sum is negative 6 as required, and it's our required eigenvalues. And how to find corresponding eigenvectors, and we should consider what our matrix multiplied by a vector is equal to lambda multiplied by a vector, and this vector is required. It's our corresponding eigenvector. So our matrix is negative 4, 0, 3, negative 2 multiplied by x, y is equal to negative 2 x, y, and we rewrite it as simultaneous equations. So it becomes what? Just multiplication. We rewrite x, y, and this by this plus this by this. So you can see that it becomes what? Negative 4x plus 0y is negative 2x. And the second row, 3x plus negative minus 2y is negative 2y. And you can see it becomes what? Negative 2x is 0 and 3x is 0. Actually, you need only one row, the second or one equation, another must be true automatically. So you can see that it to be true, x must be 0. But y may be absolutely any value, and we take what our eigenvector to be in the smallest integer, so we can take y to be 1. It may be absolutely any value, it doesn't matter, and we need it's important direction only, so we take any multiple of this vector. So our let it be p1 be what? 0, 1. And consider another eigenvalue, so it becomes negative 4, 0, 3, negative 2, x, y is negative 4, x, y, and it becomes negative 4x plus 0, y is negative 4x, 3x minus 2y is negative 4y, and we can see the first becomes just 0 is 0, and the second becomes what? 3x plus 2y is 0, and we should choose any integers. It would be better to choose the smallest possible integers so that it should be true. And we can see that we can take x, for example, to be negative 2 and y to be 3. So the second eigen vector becomes negative 2, 3. It may be 2, negative 3, it doesn't matter, it may be negative 4, 6. So the next, hence write down the general solution of a system. And actually, why do we need the eigenvalues and the corresponding eigenvectors? Because you can notice that this matrix, it's a matrix constructed on the coefficients of a given system of a couple differential equations, minus 4x plus 0y, and you can see coefficients are negative 4, 3, 0, negative 2. And if we consider a couple differential equations of the form dx over dt is ax plus by, dy over dt is cx plus dy, it's a general form. And notice that derivative with respect to time also can be denoted as with dot at top, like this. It's the same. And the general solution is given by, this formula is given in the data booklet, so it may be denoted like a vector. It means our values x and y here. X, y are what? Some constant e to the power of lambda 1 t, it's time, because it's equation with respect to time, and corresponding eigenvector p1 plus b e to the power of lambda 2t, and also multiplied by p2 vector. So for our problem it becomes x, y is some constant a e to the power of, what is the first eigenvalue, negative 2t, and multiplied by a vector 0, 1 plus some constant e to negative 4t and vector negative 2, 3. It can be rewritten again as simultaneous equations. It looks like x is a e minus 2t multiplied by 0 plus b e to negative t multiplied by negative 2. Or it would be better to rewrite as it just, you can see just what is 0, negative 2b e to negative 4t, and y is what, a e to negative 2t multiplied by 1 plus b e to minus 4t and multiplied by 3, which is a e to negative 2t, and plus 3b e to negative 4t. And as usual, to find some unknown constants here, A and B should be found in general, there must be given some additional points. For example, when t is 0, x is something, or when ty is something, or it may be absolutely any point, so you just substitute and find A and B. So it's a general solution or exact solution of a system. Determine with justification whether the equilibrium point 0, 0 is stable or unstable. You can see that we get e to negative power, or both eigenvalues are negative. And what does it mean? It means that e to negative 2t tends to 0 and e to negative 4t also tends to 0 when, or as t tends to infinity, plus infinity. So when time increases, these values decreases to 0 and our x and y values tends to 0. So we say that our system is stable, or it will be a stable equilibrium point. Origin will be stable equilibrium point, or we say just system is stable, or asymptotically. Asymptotically means when t is very large, stable, or just stable. So our system is stable. And you may guess it when e to positive power and it tends to plus infinity when time increases, so such system will be unstable. So here you write like this, or you may just write that two real negative eigenvalues, and it implies that stable equilibrium point, or the equilibrium point 0, 0 is stable, or our system, system is stable. Okay, D. Find the value of dy over dx. How to find dy over dx? You can do the next. Dy over dx is the same as dy over dt, dx over dt. You can see that dt it's like something like it cancels. Or in general, it may be useful for some problems. Dy over dx is the same as 1 over dx over dy. It's similarly to fractions. 2/3 it's 1 over 3 over 2 or something like that. Or 1/3 it's 1 over 10 divided by 3 over 10. So what is dy over dt? It is given directly. Dy over dt is 3x minus 2y. Dx over dt is what? It's minus 4x. And it's in general in terms of x and y, and we need at some points at 4, 0, dy over dx. Let's rewrite it. 4, 0, dy over dx becomes what? 3 times 4 minus 0 minus 4 times 4. It's 12 over negative 16. We can divide by 4 and get negative 3 over 4. And at negative 4, 0, dy over dx becomes what? 3 times negative 4. And negative 4 times negative 4, it's what? It's also negative 3 over 4. But what does it mean? Dy over dx, it's what? It's derivative. And what does it mean? It's gradient over tangent. It's gradient over tangent. And here it's not required, but in general, if you consider dx over dt at some point, it's what? It's rate of change with time. And what does it mean? It means that if it's positive, it means that x is increasing or is moving or is directed in positive direction of x-axis at the point. X is increasing the point. And the same for y. It actually helps us to understand in which direction an arrow should be drawn. So the next, sketch a phase portrait for the general solution for the system of coupled differential equations for x is in between -6 and 6 and y is in between -6 and 6. So since eigenvalues are both negative, it will be the next. First of all, this system will be stable, but what does it mean? So first of all, you should draw two eigenvectors, and the first our eigenvectors are what? 0, 1 and -2, 3. What is the vector 0, 1? It's 0 squares in x direction, 1 square in y direction. So this vector looks like this, and again we need only direction. It's important only the direction. So you can see that parallel to this, we draw a line parallel to this vector, and you can see that this vector is just y-axis. And another vector is -2, 3. So -2, 2 squares to the left, 3 squares up, and a line through the origin and a given point. So it's, and again we need only lines through this vector. We need direction. It's important direction only. So it's another vector. And two negative eigenvalues, so system will be stable, so all trajectories will head to the origin. So we draw arrows of these vectors to the origin because system is stable. And our trajectories will be parallel to more negative eigenvalue. So this corresponds to lambda is what? -4, and it's lambda. This lambda is -2. So our trajectories will be parallel to -4. And what does it mean? For far away, and actually we need up to -6 to 6, and from -6 to 6, something like that, it starts, or it will be parallel to this vector and turn around and goes to origin. And notice that if you draw from to the left from this another vector, your trajectories should not cross or go to the right or cross this vector. And also there are additional information that at -4, 0 and 4, 0 dy over dx, it's what? It's a gradient of our curve, so it will be gradient of our trajectory. It's -3 over 4. It's by magnitude a bit less than 1. 1 it's at 45 degrees, so it's a bit more horizontal than at 45 degrees. And also it's not necessary here because we understand when two negative eigenvalues, all trajectories will be directed to the origin, so arrow will be in this direction. But if you calculate dy over dx at negative for 0, we can see it's negative value. It means that y decreases, and you can see x is positive, dx over dt is positive. It means x is increasing y, because we are moving from left to right. X is increasing and arrow is in this direction, so y is decreasing at this point. So it looks like this, and to the origin, notice that you shouldn't cross this another vector like this. It's mistake, you don't cross this. And parallel for large t values, or away from the origin, and something like that. Something like this. And from the other side also, everything will be to the origin. And again, at for 0, gradient is negative 3 over 4, something like this. And again to the origin, and one more, something like this. Something like this. And now let's consider all possible phase portraits, and they arise from all possible eigen values. So the first situation, when both eigenvalues are negative, a system is stable, so all trajectories are moving to the origin. All arrows also are to the origin, and you draw two vectors also directed to the origin, and for far away from the origin, trajectories will be parallel to more negative lambda. And when both are positive, for example, when lambda 1 is 2 and corresponding vector is to 1, and when lambda 2 is 3, vector is 1, negative 1, such system is unstable. Why? Because if we write a general solution, e to the power of 2t plus e to the power of 3t, when t increases, e to some positive power also increases up to infinity, so such the system is unstable. And again, you draw two vectors to 1 to 1, one vector, and another vector is 1, negative 1, 1, negative 1. It's at 45 degrees, and all arrows will be away from the origin, and again origin will be involved, and all trajectories will start from the origin, y-axis. And also dy over dx at any point, or dy over dt and dx over dt also will help you to draw trajectories, but in general it looks like this. And again, it will be parallel to more positive lambda, and it's what corresponding to lambda is 2 and lambda is 3. So for a large value, so away from the origin, our trajectories will be parallel to more larger vector corresponding to more larger lambda, and we never cross another vector, so it looks like this. Oh, sorry, away. Actually, our solution also looks like this, but one of vectors it's just y vector, y-axis, so it looks like this. But in general, it will be like this. If both lambda is negative 2, lambda 2 is negative 3, it will be absolutely the same. Actually, but arrows will be to the origin, and will be parallel for points far away from the origin. It will be parallel to more negative. To negative, it will be parallel to lambda, to vector corresponding to lambda is negative. So such system is unstable. Then, if one lambda is positive and another is negative, so it will be, you again draw two vectors, and an equilibrium point, it will be a saddle point, it looks like this, and it asymptotically approaches to these vectors, and overall such system is unstable. A system is unstable. It has some equilibrium point, but in general it's not stable. And you may guess that it will move away from the origin, or it will diverge for parallel to positive lambda and move to the origin parallel to negative lambda. So it's this vector corresponds to lambda 2, which is negative, and this corresponds to lambda, which is positive, and from negative to positive. It looks like this, and you can see somewhere here it's an equilibrium point. And then if two lambda values are purely imaginary, and you remember then when you consider some equation and complex roots arise in pairs, they are complex conjugate. For example, when a plus bi is a root, a minus bi is also a root. But when a is 0 and roots are plus minus bi, so portrait looks like this. Trajectories are ellipses, or it may be some circles, and to find out in which directions arrows are, it helps what dy over dt, dx over dt, and also we can find dy over dx to find gradient at some points. So here origin is a stable equilibrium point, but not asymptotically stable. So system is not asymptotically stable. It means when t tends to infinity, system doesn't tend to some limit. So system is unstable asymptotically, but there is a stable equilibrium point, but system is unstable. Not asymptotically stable, and this origin also called a center. So origin is stable equilibrium point, but not asymptotically stable, also called a center. And if lambda values are complex, but real part is negative, so trajectories approach the origin in a spiral manner. The origin is asymptotically stable focus. It's spiral sync. So it looks like this. And again, you can find out it may be in clockwise or anti-clockwise direction. You also need what? dy over dt, dx over dt, dy over dx, or something like that. Anyway, arrows are always to the origin because it's a stable system. And finally, when lambda are complex but a is negative, so real part is negative, so the trajectories move away from the origin in a spiral manner. Origin is unstable focus. It's spiral source. Actually, it may be enough just say spiral sync or spiral source. So it looks like this. Yx. It starts from the origin and the way. Not turning back to the origin. Maybe would be better. Something like that. Something like this. Something like this. And away from the origin because system is unstable. And that's all for this question.